Have you ever noticed how some patterns just pop up everywhere? I mean everywhere, in nature, in business, even in your own life. Well, there's this one particular shape that describes an incredible number of things in our world, and it's pretty much hiding in plain sight. So today, let's pull back the curtain and uncover this hidden pattern together. So what is this master pattern? I mean, what could possibly connect the heights of people walking down the street, the birth weights of a whole bunch of baby elephants, and how much money a little cafe makes each day? On the surface, it all seems totally random, right? But believe it or not, there is a hidden connection that ties them all together. And that secret is this shape. Yep, you've probably heard it called the bell curve. And for a really good reason, it looks just like the outline of a bell. But its official name, well, that tells us just how incredibly common it really is. Statisticians, they call it the normal distribution. Why? Because, well, finding it is normal. It's so common. Think of it like a map of possibilities. It shows you exactly what's typical and what's rare. The taller the curve gets at any point, the more often those values show up. So here's the key takeaway. In a normal distribution, most of the data points just love to huddle together right in the middle, around that central peak. And as you move further away from that center, in either direction, the values get less and less likely. It basically tells you what's expected and what would be a real surprise. Now, of course, not all bell curves look exactly the same. I mean, the distribution of human heights is obviously going to look different than the one for elephant birth weights. But here's the cool part. It turns out you only need two numbers to perfectly describe any normal distribution. I like to think of them as the two control dials for the shape of the curve. Okay, so the first dial is the mean, which you'll see written as mu. This just sets the center of the curve. It's your average value, plain and simple. The second dial is the standard deviation, or sigma. And this one tells us how spread out everything is. A small sigma, like you see on the left, means all the data is packed in tight, giving you a tall, skinny curve. A large sigma, on the right, means the data is all spread out, making the curve flat and wide. And here's where it gets really practical. The spread is incredibly predictable. This is called the empirical rule, and it's like a fantastic cheat code. For any normal distribution, about 68% of your data will be within one standard deviation of the mean. About 95% will be within 2, and almost everything, 99.7%, falls within 3. This gives us a super quick way to eyeball whether a data point is totally normal, a bit unusual, or truly rare.
But this brings up a tricky question. How do you compare completely different things? Apples and oranges, or in this case, pizza sizes in inches and exam scores in minutes. What's more impressive? They're on completely different scales. To compare them fairly, we're going to need some kind of universal language.
And this is our solution, the z-score. The z-score is our universal translator. It can take any data point from any normal distribution and tell you the exact same thing, how many standard deviations it is away from its own mean. And the formula is beautifully simple. Just take your value, subtract the mean, and then divide the whole thing by the standard deviation. So what does a z-score actually tell you in practice? It's super intuitive. A positive score, your value is above average. Negative, it's below average. A z-score of 0 means you are perfectly smack dab in the middle average. So a score like negative 1.5 instantly tells you that a value is 1.5 standard deviations below the mean, no matter if you were talking about inches, pounds, or dollars.
Okay, enough theory. That's all great, but how does this actually help us solve problems in the real world? Let's put this whole thing to the test with a delicious example.
All right, picture this. Your local pizza place has a guarantee. If their large pizza is any smaller than 16 inches, you get it for free. Now, from your extensive personal research, you know their pizzas average 16.3 inches wide with a standard deviation of 0.2 inches. So the big question is, what are the odds you're getting a free dinner tonight? Here's the golden rule for solving these kinds of problems. First, always sketch a quick bell curve to see what you're looking for. We want to find the chance of getting a pizza smaller than 16 inches, so we're shading the area to the left. Second, we calculate that z-score. We just plug in our numbers, 16 minus the mean of 16.3, and divide that by the standard deviation of 0.2. And that gives us a z-score of negative 1.5.
And that z-score lets us find the answer. It corresponds to a specific probability. There's a 6.68% chance of getting a pizza that's smaller than 16 inches. So hey, the odds aren't huge, but a free pizza is a free pizza. I'll take those odds.
Now, understanding z-scores is absolutely crucial. But let me let you in on a little pro tip. Your calculator can do the heavy lifting for you.
Most scientific calculators have functions like normal CDF or NCD. You can just plug in your values, and it will find that area under the curve, that probability, for you in a split second. It's the engine that does all the hard math.
So far, we've gone from a value, like 16 inches, to a probability. But what if we need to do the exact opposite? This is where you really start to level up your skills, and it's a move that's essential for tackling more advanced problems. Let's completely flip the script. Imagine you already know the probability, but you need to find the cutoff value that goes with it. For example, let's say a school wants to give an award to the fastest 10% of students who take a test. What's the maximum time a student can take and still get that award? For that, we use the inverse workflow. And you guessed it, your calculator probably has another magic button for this, often called inverse normal or INVN. It's built for exactly this scenario. You feed it the area, in our example, the fastest 10% or 0.10, and it spits back the boundary value, the exact exam time that separates the top 10% from everyone else.
And here's the ultimate power move. You can use the same inverse method to find a missing mean or a missing standard deviation if you don't know it. The trick is to first use that inverse normal function to find the z-score. Then, you can plug that z-score back into our original formula and use a little algebra to solve for the missing piece. It's a multi-step process for sure, but it shows you've really mastered this stuff.
So in the end, what's the big deal with a bell curve? I think this quote really nails it. It gives us a common language, a framework to make sense of data, to see the pattern in what looks like chaos, and to describe just how normal or how truly exceptional any given thing really is. So the only question left is, where are you going to see it next?